Most rocket engines ignite once. They fire on the ground, they push the rocket through ascent, and then they shut down forever. But Apollo needed an engine that could go beyond that. It needed an engine that could fall silent, drift in Earth orbit for nearly 3 hours, and then come roaring back to life in the vacuum of space to send astronauts toward the moon. That engine was the Rocketdyne J-2. It powered the Saturn V's second stage and the Saturn V's third stage, the stage responsible for translunar injection, restarting a cryogenic liquid hydrogen and liquid oxygen engine in orbit was one of the most demanding engineering challenges of the entire program, and even today, it remains cutting edge. To restart the J-2, NASA had to control boiling hydrogen, settle floating propellants, condition an engine that had been freezing in space, and ignite a hydrogen flame in a completely airless environment. And the entire sequence had to work on the first try. If the second burn failed, the mission never left Earth orbit. Today, we are going inside that engine to see how Apollo engineers made the impossible routine. The J-2 produced roughly 230,000 pounds of thrust in vacuum and burned liquid hydrogen at around -423 degrees Fahrenheit and liquid oxygen at around -297. The chamber pressure sat around 800 pounds per square inch, and the nozzle expansion ratio let the engine breathe efficiently in vacuum. But the defining feature of the J-2 was its restart capability. The Saturn V's third stage, the S-IVB, had to ignite once to reach parking orbit, then later ignite again to perform translunar injection. That second burn depended entirely on the J-2 starting cleanly in zero gravity after sitting dormant in the harsh thermal environment of space. Early test flights revealed issues, especially during Apollo 6, when the S-2 and S-IVB both experienced problems. But after these issues were corrected, the mature J-2 configuration performed reliably across the operational lunar missions. In microgravity, propellants float. They do not settle at the tank outlets the way they do on Earth. A cryogenic turbopump cannot ingest bubbles. Vapor ingestion leads to cavitation, surges, violent vibration, and immediate loss of thrust. To solve this, the S-IVB used its auxiliary propulsion system, or APS. These were small bipropellant thrusters using monomethylhydrazine and nitrogen tetroxide. When the restart sequence began, these APS thrusters fired gently, producing a small but steady acceleration that pushed the liquid hydrogen and liquid oxygen toward the bottom of their tanks. It did not take much, just a small fraction of a G, but it was enough to build the head pressure the turbopumps needed. Earlier Saturn stages used dedicated solid ullage motors, but for translunar injection, it was the bipropellant APS thrusters that made the restart possible. Without ullage settling, the J-2 would ingest vapor, lose prime, and fail before it ever fired. Liquid hydrogen is the most difficult propellant ever flown. Even inside an insulated tank, it boils constantly. Heat leaks into the tank from the sun, from earthshine, from electronics, and from the engine's own thermal mass. During the parking orbit coast, the S-IVB had to maintain stable tank temperatures and pressures. This meant venting boil-off through carefully controlled valves and using slow, deliberate attitude maneuvers to prevent hotspots and uneven heating. This was not the same as the spacecraft's famous barbecue roll,
which was associated mainly with the command and service module and the lunar module on their translunar coast. But the third stage did perform controlled roll maneuvers and venting to keep the cryogenics within operational bands. Thermal management during this period was critical. Too warm, and the hydrogen density changed enough to affect pump performance. Too cold, and valves or lines could freeze. Restart depended on the entire system being thermally conditioned.
Before the J-2 could ignite again, the engine had to be brought back into the correct temperature range. Even a short period of coasting could leave liquid hydrogen warm enough to flash boil inside cooling passages. To correct this, the engine used a several-minute conditioning sequence. Valves opened, and both liquid hydrogen and liquid oxygen were bled and recirculated through the engine's cooling channels, turbopumps, and feed lines. Liquid hydrogen did most of the thermal work, chilling the engine down to the correct temperature so that the pumps would flow a solid, stable column of propellant. This lengthy bleed ensured that the engine was cold-soaked and purged of vapor pockets. It was the only way to guarantee a clean, stable ignition.
Igniting hydrogen and oxygen in the vacuum of space required more than a simple spark. The J-2 used an augmented spark igniter, the ASI, a small, dedicated pre-burner chamber built right into the engine. Here is how it worked. Spark exciters energized spark plugs inside the ASI. A controlled flow of hydrogen and oxygen entered this igniter chamber. The spark lit the mixture, producing a continuous, stable flame. This flame then shot into the main combustion chamber, igniting the full propellant flow. This igniter was not a single-use pyrotechnic cartridge. It operated through the entire burn, and its design allowed multiple starts. The use of spark plugs rather than pyros was one of the key features that made the J-2 reliably restartable. Without the ASI, ignition in vacuum would have been unpredictable at best and catastrophic at worst.
The J-2 had two turbopumps, one for liquid oxygen and one for liquid hydrogen. They were driven by a gas generator that burned a fuel-rich mixture of hydrogen and oxygen. During a restart, helium control systems activated purge flows. The start tank released stored energy to spin the turbines initially. The gas generator lit using its own dedicated spark system, and the turbopumps accelerated smoothly to operating speed. The restart sequence depended on precise timing. A premature flow of propellant could quench the igniter. A late flow could produce a hard start, an overpressure event inside the chamber. And any vapor ingestion could cause turbopump cavitation. The engine had to wake up in the right order, with the right pressures and in the right thermal condition. When everything aligned, the chamber lit smoothly and the engine settled into its rated thrust.
The J-2 operated at a mixture ratio around 5 to 5.5 parts liquid oxygen to 1 part liquid hydrogen by mass. This ratio maximized performance while keeping combustion temperatures within safe limits. During restart, the mixture ratio had to be controlled carefully. Hydrogen warmed during the coast, oxygen stratified slightly, and both had different densities compared to their first burn. Too much hydrogen cooled the chamber excessively, reducing thrust. Too much oxygen drove temperatures up and risked hardware stress. The engine's valves adjusted flows continuously, keeping the flames stable throughout the burn. Compared to the brutal F1 engine, the J-2 was more delicate, but that precision was the reason Apollo could fly to the moon.
When the moment came for translunar injection, the spacecraft and third stage oriented themselves, the APS ullage thrusters fired, the propellants settled, the cryogenic conditioning sequence completed, the ASI ignited, the gas generator came online, the turbopumps spun up, and finally the main valves opened. In a single heartbeat, the engine erupted into life, pushing with 230,000 pounds of thrust. The astronauts felt the acceleration instantly. The Earth fell away beneath them, and the spacecraft committed to the 3-day journey to the moon.
Even now, restarting cryogenic engines in orbit is a challenge. Hydrogen boil-off, thermal gradients, propellant settlement, and ignition stability all remain difficult problems. Modern upper stages, like those powered by the RL-10, still use long conditioning sequences, ullage thrust, and careful attitude control. Large cryogenic stages, whether hydrolocks or methyl locks, still face many of the same constraints that Apollo engineers tackled with the J-2. The technology has advanced dramatically, but the fundamental physics have not changed.
The J-2 did not fire flawlessly on every single mission. Early flights uncovered issues, including the Apollo 6 restart failure and S2 anomalies. But after the ignition system improvements and design refinements, the engine's performance during the operational lunar missions was excellent, and it became one of the most important pieces of hardware in the Apollo program. It was the engine that bridged Earth orbit and translunar flight. The engine that proved a cryogenic rocket could sleep in space, then wake up and change the destiny of a mission. And the engine that powered the burn that sent human beings beyond Earth for the first time. The J-2 remains one of the great achievements of Apollo engineering, elegant, complex, and decades ahead of its time. If this video helped you understand how the J-2 engine came back to life in orbit, hit the like button and share it with someone who appreciates real engineering. It helps the channel grow and keeps these Apollo deep dives coming. Thanks for being part of the mission. See you in the next one.